All right. It's a pleasure to be here and to tell you about what I think are exciting developments going on in the theoretical physics of gravity, understanding gravity more fundamentally. The title says Emergent Gravity. Indeed, we're trying to understand better where the equations of general relativity are coming from, and there seems to be a link with the language of quantum information. Now, what I'm going to present in this talk is something that I believe will then come out of it, namely that we can understand better than questions having to do with dark energy and dark matter, so that's the dark universe. Of course, we have already an excellent theory of gravity in general relativity, and it has been tested in many situations, in particular in, recently the detection of gravitational waves, in other events with strong gravity in particular, and already in the solar system we have many tests. So it's not easy to change it because it also is a very beautiful theory. It's based on all kinds of nice principles like the equivalence principle and coordinate invariance. Yet there are phenomena where we have to assume the existence of more matter if we want to make sure that general relativity works, for instance, in these kind of strong lensing observations or weak lensing in clusters, or in explaining the rotation curves of galaxies. This is indeed done because we believe that there's no real reason why general relativity would fail. I think that story might eventually change if we understand better indeed what gravity is. And I'm going to indeed tell you something about these observations in galaxies in particular that seem to hint that there may be a relationship with understanding with this idea of emergent gravity. So looking at larger scales, of course, we see evidence for dark matter as well. I already mentioned clusters, and if we go to the entire cosmos, eventually by analyzing the cosmic microwave background, we get to this picture that there is a lot of dark energy, it's 70%, about 25% dark matter, and then only 5% is in the form of ordinary matter that we know in terms of baryons. Here I also indicated the photons, which are the photons of the microwave background. And the reason is that I am not only interested in how much energy is contained in each of those components, but if you ask how much entropy is contained, what's the amount of information you need to describe all of these objects, where they are, and what's contained in what's the entropy, turns out the photons, according to current theory, carry most of the entropy, namely about 10 to the 90. But I think that is not the full account. I mean, there are other objects that carry entropy, like black holes, and they would add up to a little bit more. But for instance, a dark energy is usually seen as just a fluid without much entropy in it. I'm going to claim that if you think about emergent gravity, actually most of the entropy in our universe is actually contained here, and that will change the way we have to think about gravity. So indeed, my conclusion is going to be that if we look at our universe, I'm looking at it sort of from the point of view of our galaxy, from the middle. Then if we look outwards, the universe is expanding, and then when it starts expanding with the speed of light, I call this sort of the Hubble radius, and that's sort of the farthest we can see. It's like a horizon. And I will argue that there's actually an entropy inside this universe carried by the dark energy, which has this number, actually a much larger number than that of the photons. And that will affect what's going on inside the galaxy. In particular, I'm going to, just for simplicity, assume if the universe would only have dark energy in it, we would live in a universe that's called de Sitter space. And this would be what it looked like. It has a horizon determined by the Hubble parameter. This is the parameter that tells you how fast the universe is expanding. And if we would write down a metric, it would look like that. I'm thinking of ourselves or our galaxy to be sort of in the middle. Our galaxy would be much smaller than this picture. I mean, the horizon is like 10 billion light years away or more, and our galaxy is much smaller. And yet, if we look at our galaxy or other galaxies, they do something funny in the sense that if we look at the rotation curves, that's the velocity as a function of the distance. You see that they follow what you would expect Newton would have predicted, or Einstein, based on the matter that we see. So we only look at the stars that we see and we calculate their mass, and then you determine that the velocity should go like this. But what is observed is that the velocity sort of flattens out. You get these flat rotation curves. And the only way to explain this discrepancy is by adding more matter, which is then the dark matter that people say is contained in halos around a galaxy. Now, the funny fact is that if you look at this point here, where the curve starts deviating from the Newtonian prediction, it always happens at a certain acceleration. So if you calculate the acceleration, it always happens when it falls below this value, where h is again the same Hubble parameter. And that's kind of unexpected because, as I told you, the galaxy is much smaller than the universe, so why would it know about this number? Even the expansion is going so slow, but apparently there's some reason why this happened. Actually, this observation was made by Milgram already about 30 years ago. So this suggests maybe some connection. And the thing I'm going to talk about is indeed this idea of emergent gravity. And this comes from thinking about gravity in different circumstances, in particular near black holes. Well, in the previous talk, we already heard a lot about black holes, that they have horizons, and it's Bekenstein and Hawking that already concluded from thinking about their quantum properties and by looking at certain thought experiments that black holes must have an entropy. What is moving here? Well, I hope it doesn't disturb you. Anyway, the entropy is proportional to the area of the horizon, and it has a temperature proportional to the acceleration at the horizon. And then it turns out that the Einstein's equations can be sort of cast in the form of the first law of the thermodynamics. So if you calculate using the Einstein's equations what happens to the area of the horizon when you change the mass, it turns out it's this equation. But this equation with these identifications becomes the first law of thermodynamics, just dE is TdS, which we know can be described or even derived from a microscopic theory. It's just derivable from statistical physics. So if we know the origin of this entropy, we might actually derive this equation just by the usual statistical methods, and then we have a way of deriving the Einstein's equations. That's the idea of emergent gravity. So emergent gravity tells you that there must be a microscopic picture that explains this entropy from which gravity can be derived. In particular, the Einstein's equations can be derived, and this is the aim of this whole program. And so the essence comes from these ideas of Bekenstein and Hawking on black hole thermodynamics. So I mentioned already there are thought experiments, and I'm going to actually mention one of those, or actually go over one of those thought experiments due to Bekenstein, which I will need in a minute, because it tells me something about the amount of entropy that you can associate with a mass inside a certain radius r. So here I have a box with mass inside, and I lower the box into the black hole. And the question that Bekenstein asked is, how much entropy can there be inside this box, given the mass and the radius? And the thought experiment is just putting the box inside the black hole. The black hole will increase its size a little bit. Actually, it increases its size according to the first law. And by calculating the amount of work that you do by dropping the box in, where the force is just the Newtonian gravitational force, you calculate the change in entropy. But this change in entropy should be smaller, or larger actually, than the amount of entropy that can be inside the box. This gives you a bound. Namely, the nice thing of this calculation is that the temperature is expressed in terms of the acceleration, but the force as well. And then the acceleration drops out, and you're left with an equation that tells you that the entropy can be expressed as a product of the mass and the radius, and just the natural units of c and h bar in there. It is independent also of Newton's constant, but it tells you something about this entropy. Actually, this formula will come back later in the talk. That's why I mentioned this. So talking about these ideas of emergent gravity is something that comes out of string theory. And string theorists, they don't think so much about the universe with a positive dark energy. They like to think more about a universe which is the one without any dark energy, or actually a negative cosmological constant. I said there was a space, the Sitter space, which looks like this, which has a cosmological horizon. That's the one closer to what we live in. But string theorists in particular like to think about this space, which is called anti-de Sitter space, and it changes, the difference is just that the minus sign becomes a plus sign. But this space has no horizon, it even has a boundary. At infinity here we have no boundary. And it has properties that we like, because this boundary is something that we can use to put a microscopic theory on, so that we can explain the gravity inside. That comes out of string theory. It's related to what's called holography. And those developments actually come from these ideas of Bekenstein and Hawking, because there the area is actually like the horizon area is like sort of the boundary of this region. And here these ideas have sort of been made more concrete and actually quite precise. We can derive gravity inside this space by a microscopic description on the boundary. So this goes under the name of the ADC-CFT correspondence, where on this boundary we have put this conformal field theory, and we find that the gravity in the bulk can then be derived, sort of emerges really like an emergent gravity from this microscopic theory on the boundary. And one way to think about this boundary is that we have, or the extra direction, I should say, perpendicular to the boundary in terms of some scale where we go from the ultraviolet to the IR scale, and this is the way that the bulk sort of contains the gravity. Now, what people have shown in this context, indeed, that we can derive Einstein's equations precisely according to what I just told you about, using a first law of thermodynamics. And it has to do with an entropy that people can define in terms of quantum information concept, in particular an entanglement entropy, which obeys this precisely the law that Bekenstein and Hawking said, namely, if I take this region on the boundary, you can associate a certain entanglement with it, a quantum quantity that's expressed in terms of a surface area of some inside the space-time, and it satisfies this equation. And then if you write down this first law, you find that you can derive the general relativity equations, but you have to assume that it satisfies this area law. So there's sort of a condition that you have to put in, and then you get back to the Einstein's equations. This is a whole development going on. It goes back to ideas of John Wheeler, who said that quantum information, or information itself, is actually the basic building block from which we can derive space-time even, or matter, so that's called it, from qubit. And that is, as I said, a real community of theoretical physics working on these ideas of emergent gravity, where we take quantum information to be our starting point. And we use things like entanglement entropy to sort of derive then the geometry of space-time. So I'm going to actually now go back to the Sitter space and tell you a little bit about what is different there and what I think then will change to these gravity equations. So if we take our universe inside this big horizon, so I told you there's a horizon determined by the size of the Hubble constant, and then there's also an area of that horizon, because I'm going to apply the same logic as that Bekenstein and Hawking did to the horizon of a black hole. Actually, the equations are very similar. Actually, Hawking and Gibbons showed that indeed you can associate an entropy to this horizon, which is again given by the area divided by the Newton's constant. So it's exactly the same expression. There's also a temperature, and that temperature contains the Hubble constant in it. It's a very tiny temperature. It's not like you get a hot, well, this temperature is incredibly small, but the entropy is incredibly large. Actually, this is the 10 to the 120 that I talked about, and that entropy is due to the fact that there is a positive dark energy in this universe. So when there's no dark energy or negative dark energy, there's no horizon, and you would not have this equation. So I associate this entropy and the temperature actually due to the dark energy. And that will help me actually explain some of these properties. So what I'm interested in now is thinking about the gravitational interactions that will take place, or how I think about gravity when I add to this universe with dark energy some matter, in particular some galaxy, say in the center. And what I will show is that there's actually a way of understanding what happened to those galaxies by thinking about this entropy associated to this dark energy. Namely, if I go back to my observations that I told you about, that if I think about where does this deviation start to happen, it happened when the acceleration fell below this number in terms of the Hubble constant. So the Hubble constant already appeared also on the previous slide in the temperature, but it also actually determines the radius, so it appears in various places. So there's one way I can think about this equation, namely I can rewrite it a bit by thinking about putting a radius somewhere here, so that's the radius r. Then I can translate this into an area, because the r squared actually goes like an area. So that's the 4 pi r squared. Then I put in some other constant like h bar on both sides, so actually it would drop out. But this equation is the same as this equation. But what I've written here is an energy divided by the temperature that I had on the previous slide, this temperature. So this is an entropy divided by temperature, an entropy. And here I have again a relation that's exactly the same equation again. It's the area divided by 4g. So this is also an entropy. And so apparently when this number becomes smaller than that, this is when this is happening. And I'll indeed already tell you there is some idea that actually this comes from these, well, you see already from this equation there may be some hint towards this emergent gravity ideas. Actually, there's one observation I like to mention immediately, is that if you add matter to this galaxy with only dark energy, the horizon size becomes slightly smaller. And this is because adding mass adds a term in the geometry which gives you a new location of the horizon. And if you calculate the change in the area of the horizon, it's precisely this number, mc squared over this temperature. So it's the same equation that I had here. And this is the change in the area of the horizon, which sort of appears on the same side as this equation here. This is, by the way, this is a phenomenological observation about where these things happen. This is an equation that I can derive by thinking about the entropy in the de Sitter space. And so again, there's some connection between maybe the change in entropy and where we see these things happening. So adding a galaxy inside this universe will change the entropy of it, of this universe. Now, how do I get now to my phenomena associated to these rotation curves? I actually am going to assume that this entropy associated to the entire universe is going to be divided over the entire space in such a way that, namely, it's like a constant entropy density. The reason is that the dark energy itself is also a constant energy density, and I told you the temperature and entropy are associated to that, so I'm also going to assume there is an entropy density. But that entropy density must be such that it adds up to this entropy when you integrate it over the entire volume. So what I've done here is actually written down an expression for an entropy that grows like the volume, because, well, the area multiplied by r is growing like the volume. But I've chosen the normalization in such a way that if I put r equal to the radius of the entire universe, that this number becomes equal to that number. And that's easy to see, because this factor becomes 1. But I'm going to take this in a much smaller region, so I know how much entropy is actually localized in this region. So let me now go back again to these observations. So I now rewrite it one more time. And then I see that the same equation here, I've changed notation from little r to capital R, but for the rest it's the same thing. I actually wrote down an expression here which contains again the mass, and this is again the area. But this equation has the following interpretation. This is the amount of entropy that I told you that is associated to the dark energy inside a certain region. So say I take some part of this galaxy, I take a little radius sphere around it, then this is the amount of entropy that the dark energy would contain. This is the entropy that Bekenstein calculated associated to the mass inside a certain region, well, in terms of the mass and the size of the region. And if this becomes smaller than that, this is where this starts deviating. So this has a very natural interpretation, because this is entropy that I can associate to any matter that came out, well, that is inside a certain region. This is the entropy in the dark energy. So I'll interpret it like this. There's actually a matter actually has a sort of entanglement, has an entropy associated to it, and this observation becomes this equation. And this is the left-hand side is what sort of the entanglement or the entropy that matter takes away, and the right-hand side is then what is contained in the dark energy. And it's basically this picture that mass takes away part of the entropy that's associated to the dark energy, and it empties it. But as soon as this becomes smaller than that, we have a space where the dark energy contains an amount of entropy, and that's going to change these rotation curves. I'm going to make that even more quantitative. So what's happening here can be actually plotted in the following way. So I'm going to look at the acceleration due to the baryons. That's what we see. That would be this curve, but then translated into an acceleration. And this would be the observed one, which is the other curve above here. Turns out there's a very tight correlation between the two, and this is known as the radial acceleration relation or the mass discrepancy acceleration relation. And it has the following shape. Here I plot the logarithm of the baryons, the acceleration due to the baryons. And this is the logarithm of the observed acceleration. And here are about this many measurements, which I think in total are about 170 galaxies that have been used. And they put all together, they all fall on a same curve. There's some scatter around it, but the correlation is pretty tight. And so if you take the distribution of all the points around it, you find a natural Gaussian distribution with a certain width. But if you look at the curve here, what it tells you is that if you know the amount of baryons, you can determine how much dark matter is there. Of course, you can say the other way around. If I know this acceleration, I know how much baryons there are. But the baryons is a very tiny fraction. Why would that be so tightly correlated? And there's some way that this seems to imply that if you know how much baryons there is, you know what the acceleration is. Again, this is also observed by people like Milgram, and actually this comes from a paper of Markov, who has also worked on this modified Newtonian dynamics. However, in this paper they make the point that this has nothing to do with Mond. It's basically a relation, an empirical relation, which holds for many decades, actually for a long set of values, a large set of values of the acceleration, because it's describing the lower one. If these two would be equal, of course, the Newtonian answer would be the straight line, and this is the deviation. And there is a linear relation that's holding for low acceleration. Namely, if you take the square of the observed velocity, you can relate that to the baryonic one. This actually has a name. It's the Tilley-Fisher relation, and it also is implied by Mond. Modified Newtonian dynamics, although it's not written down as a law here. Here it's really an observation from empirical relation. So I want to explain this one from the ideas I just described. I'm not going to do that calculation, but I'm going to give you the idea. Actually, there's some way I told you that we can derive the Einstein's equations from these ideas of entanglement. And for that, it was very important that we have this Bekenstein area, Hawking area law. That's actually true in the space that string theory is like, it's in anti-de Sitter space. But when we have a positive dark energy, this is where I say there is actually a excited state with a positive entropy density, which does not obey this area law. And actually it gives you additional, well, not just energy density, but as I said, also an entropy density. And you have to think about this picture, that the dark energy contains entropy, but the matter has removed part of it. And so there's this region around it where the matter basically takes the entropy of the dark energy and puts it all in one location. If you then start calculating these emergent laws of gravity, you will find a deviation that has to do with the entropy density, and it sort of works like elasticity. It sort of pushes back, namely because it has been removed here, it tries to push back, and that pressure you can calculate actually quite, there's a quantitative calculation you can do, and which I'm not going to actually explain because of the time, but sort of this is the picture I use also in more popular talks. So here's the galaxy, and then there's the information associated with the dark energy around it, which has been pushed away, but that sort of affects the rotation curves of these galaxies. And eventually, when you go through the calculations, you actually get this relation. It's an estimate of the energy contained in the in the gravitational field. So if I take the acceleration and I square it, it's like what you do with an electric field when you square it and integrate it over the volume, you actually calculate the energy density contained in the gravitational field in the Newtonian fashion. And indeed you have to multiply, divide by 8 pi g, just like what you do in electric fields. If you integrate this over a region of size r, capital R, you get exactly the expression that's, well, again, the same relation that Bekenstein had, mcr over h bar. So here I only have the baryons, while here I write down the total acceleration, also including the dark matter. So there is a relationship that you get that if you then derive what that implies for the acceleration for the observed one in terms of the baryons, well, you have to differentiate with respect to r and get some way of relating the square of g to then an expression actually that will turn out to be also related to the acceleration. Namely, these are these curves that McCoff and others found. There's some way of matching it. Actually, there's some way it depends on the radius, and actually this is the way in which it fits better. They had to adjust a little bit the mass to light ratio, but this comes from just the simple ideas I just explained, but this already confirms part of the observed relation that's seen. And for me the main point is indeed that I can derive these relations from this idea, actually from the way that I've talked about or even think about the dark energy playing a role. There's a further test that actually go much larger distances. It have to do with the fact that when you look at galaxies, when you go further out, you don't see any stars going around. So it's very hard to determine the gravitational field away from the center. You can do it by weak lensing. So if you have weak lensing, you look at the distortions of background galaxies due to the gravitational potential of, say, a foreground galaxy. And those distortions can be measured much further distances. Well, it's kind of a hard measurement to do, and this is why there's a statistical way people do it. They combine many galaxies together, then you have your scatter and your errors. But anyway, you see a trend, which is again on a log-log plot. Here they put it on 4 different mass ranges, and the predictions of the theory are the blue lines. And they fit quite nicely for all of those 4 ranges. Here, again, I put actually all of those data points together in a similar plot where I take here the baryonic expectation. This is what observed, and you see a correlation that the theory would predict, which fits quite well with what is being observed. Actually, it's the same relation again that was found for galaxies at much smaller radii. So it appears to hold. If you now look at the range of radii, it's about 3 decades, 3 powers of 10 that you can multiply, which is quite a large range that is hard to explain with just conventional dark matter models. So this is sort of where I finish. I mean, I want to say a bit about what questions have still to be answered. So this is some effects that are all related to dark matter. So people have done a lot of simulations, for instance, also thinking about clusters. So here, this is the bullet cluster where you see the gravitational field moving apart from where the baryons are sitting. These are things you need to explain. Or mergers. Or this is what's called baryonic acoustic oscillations, which has to do with the distribution of baryons in our present observations and how they came about from the fluctuations that we see in the cosmic microwave background. These are all things that need to be explained again without the dark matter that people add, or maybe in the way by using the equations that I have. This is still in development because there are equations that need to be solved here which are more dynamical, where things start depending on time, and this is a hard thing to do still. There's also, of course, the observations of the CMB that have a prediction, because this is the supernova data, this is from clusters, and this is from the CMB, and then if you combine it, you get some prediction of how much matter there is. Well, that, of course, is a question we also need to address, and I've done part of that by rewriting the equation that I showed you in a way that it predicts a correlation between the amount of baryonic matter and, again, dark matter. This number is the sum of both. And so if we know baryonic matter, we can sort of deduce how much dark matter there is because of this observation. But I've done it in a different way. Actually, I find from my equations this relation. Indeed, the dark matter, the square of it, is related to the baryons. And this relation I've plotted here, and that fits very well with the data, because this is what Planck and WMAP would give us. So the same relation that fits rotation curves, as well as does very well in galaxies clusters, seems to also be consistent with this. But again, there is also a question of time dependence, because this is one measurement we have done in our present day. So how does this depend on time is still an open issue. So this is just my conclusion. There is some way we can try to derive Einstein's equations or gravity from a first law, like what we do in thermodynamics. And then the Einstein's equations require a law, namely this Bekenstein-Hawking area law. However, if we add this volume law in terms of the entropy density associated with dark energy, there are some modifications, and they have to do with some slow dynamics that happens in this dark energy. And this can give then a natural explanation of these observed relations. And of course, there are still questions which need a study of more dynamical equations that need to be solved. Anyway, that's still under investigation. Thank you very much.
Thank you, Erik, for this thought-provoking proposal.